we're going to, I think, try to start and finish Chapter 5 today. Chapter 5 is about a lot of stuff about acid-base chemistry. Chapter 5 spends a fair amount of time telling you how they determined pKa's for things that are either more basic than hydroxide or more acidic than hydronium. And I feel like that's interesting from a science history point of view, but I don't know that it's anything you'll ever need to know. And if you do need to know it, it's in that part of the chapter, so you can go to it. So we're not going to talk about how pKa values are bootstrapped. We are going to talk about the leveling effect of water. We're going to talk about some pKa trends. In particular, we're going to focus on the effect of solvation and the environment. And we'll contrast some things we know about pKa's in solution versus pKa's in the gas phase. Some things that I actually didn't know. Yeah?
Do they measure pKa's then by looking at the pH at which something is charge balanced?
Well, you can do that. You can measure pKa by experiments in water, but only for things that have pKa's between about 15 and 0. You get, okay, now it says press here to operate system.
Because, yeah, in biochemistry we learned about how they do that for amino acids.
So what they end up doing, press here to operate system, please wait. All right. Sorry. What they end up doing is they take an acid that you can measure in water, characterize it by an organic phase method, and then compare that to another results from the same experiment for another acid that you can't do in water, and based on that you can make a comparison. So all the pKa values that I will cite, I beat you. All right, sorry. We are now good to go with the screen in class. Samantha joining us remotely. Sorry for all of the hemming and hawing and stuff. We had some technical difficulties here. Okay, but all the
confused.
Yeah. So we're ready to go. All of the pKa information that we'll talk about will be in will be relative to values in aqueous phase, even though you cannot determine pKa values of 50 or 44 or even 25 in aqueous phase. So your book talks about something called the leveling effect of water. And that is that for example, HCl in water, pK of HCl has been determined to be like -9. So if you put it in water, HCl is actually hydronium, which has a pKa of around -2. Your book gives you to 2 decimal places, and I don't think we care that much. But what this means is that instead of aqueous HCl being HCl, it's actually just hydronium and chloride. And actually, there's good evidence that hydronium is actually a proton shared by multiple waters, where N is around 8. And they can tell this because of some experiments that we'll talk about in a little bit. So you can't measure the pKa of hydronium in water. Similarly, if you're using a base that's stronger than hydroxide, here you've got water pKa equals 16. Again, you've basically got quantitative conversion of T-butoxide into T-butanol and hydroxide. pKa of T-butanol is around 19. We'll talk about why it's actually higher than that of many alcohols. But again, you put that in water, and what you actually just did was make hydroxide. So hopefully you can be smart about your use of acids and bases. This is why when you're doing aqueous workup of reactions, you're using very simple things like 1 normal HCl or bicarbonate. It doesn't make any sense to use any fancier acids or bases because for the most part, all you got in water is hydronium and hydroxide anyway. All right. At least for bases stronger than hydroxide and acids stronger than hydronium. So that's the leveling effect. A related issue is that pKa values and trends can be different in water versus non-aqueous solvent versus gas phase. And this is because as we've seen, acidity often involves the formation of ions, right? And so water, because of the non-covalent interactions available to it, like hydrogen bonding and other dipole types of interactions, is extremely good at solvating ions, whereas many non-aqueous solvents are, remember, water is both a donor and an acceptor of hydrogen bonds. Some non-aqueous solvents aren't donors and or acceptors of hydrogen bonds. And then some of them don't have large dipoles. And what this means is that non-aqueous solvents are less good at stabilizing ions. And in general, acid-base chemistry involves ion formation. If you're going to donate a proton to something, in a lot of cases, you're going to get something that's positively charged and something that's negatively charged. So pKa trends can be very different. And in general, if you were going to predict, if you've got an acid in water versus an acid in a non-aqueous solvent, where is the acidity going to be stronger? Okay, that's all right. Where do you predict acidity will be stronger for a given acid, in organic solvent or water?
If you consider acidity the ability to donate a hydrogen, it'll be more likely to donate the hydrogen if its conjugate base is stabilized. So I suppose water.
Right. Water is good at solvating, and remember, solvating is a stabilizing thing. Good at solvating and stabilizing the conjugate base of our acid. So what we generally observe about non-aqueous solvents is pKa's are higher. And we also observe that pKa's are more spread out over a wider range of values. And this is because water tends to mask some differences in acidity. It's so good at solvating that some differences in acidity stop mattering quite as much. So you can think of water as the great equalizer, which sounds a lot more noble than perhaps it actually is. Whereas in organic solvent and in the gas phase, you're going to get pKa's that represent perhaps more the intrinsic stability of the conjugate base or the intrinsic acidity of the acid. I guess I will mention, and this is a 351 thing, that in most cases as we talk about acidity, we're going to be thinking about the stability of the conjugate base. There's one exception to that when we're talking about positively charged acids with neutral conjugate bases. We can still think about the conjugate base and we'll get to the right spot, but it's often useful to think about the charged species. And so we'll need to talk about that a little bit later, especially for ammonium type acids. So let me show you a little bit of pKa data. This is in your text, and it's likely not that useful for you to write down, but I just want to show you a couple of examples. Acetic acid and paranitrophenol. And we're going to show you pKa values in water, methanol, DMSO, DMF, and acetonitrile. So we're going from protic polar solvents to slightly less polar protic solvents to DMSO, which is a polar aprotic solvent, DMF, polar aprotic, and acetonitrile starts to be more nonpolar than DMF. And if you look at the pKa values just for acetic acid, in water it's about 4.8. In methanol, 9.5. That's almost a 100,000-fold difference in acidity just because the solvent polarity is different. What do you conclude there? Methanol is not as good at stabilizing the positive and negative charges that form when acetic acid donates a proton to the solvent. Or it could reflect the idea that maybe the oxonium ion of methanol is not as stable as the hydronium ion. Yeah?
In order to know how meaningful that is, it would be good to know what the KW or the analog is for methanol.
Yeah, that'd be interesting to know what the KW value is for methanol, and I don't know if people have identified that. Though I will say these numbers, though measured in methanol, have been converted into numbers that are correctly relative to pK values in water. So the comparison is fair.
Okay.
Yeah.
So in each of these cases, is acetic acid donating its proton to the solvent, or is it just exchanging a proton with itself?
That's a good question. You're asking, well, could acetic acid do this? We're going to see that protons attached to carbonyl oxygens have pKa's generally less than -2. So that if you can do something like this, where the pKa is -2, then protonating the oxygen on the carbonyl is going to be less favorable. To say nothing of the fact that you've already got the negative charge there, and actually, that's just proton shifting. Like,
Well, I was thinking of acetic acid molecules.
oh, you want? I'm sorry, you want this one?
Are they acting as? Well, I was thinking OH2 on the end of it, leaving a carbonyl left.
Okay.
But that's just.
Or having something there. Yeah, the pKa's for protonated carbonyl compounds are lower than pKa's for protonated alcohols, at least. So but that is a good question. What is it for DMSO? Well, DMSO, you can write a resonance structure like this, so it's probably the negatively charged oxygen. What is it on DMF? I don't know. What is it on acetonitrile?
Is the proton getting donated to acetonitrile or another acetic acid?
Yeah. And in general, they've done these experiments with indicators, and so it's a bit confusing as to what the right way to think about it is. I think the general idea we want to get is that the more nonpolar the solvent is, the less good it's going to be at stabilizing charged conjugate bases. So you'd expect the pKa to be even a little worse in DMF than DMSO, and that is indeed what you see. paranitrophenol has a pKa of like 7.2. In methanol, it goes up again by almost 10,000 fold. Doesn't make a huge difference going to DMSO, a little bit less acidic in DMF, hugely less acidic in acetonitrile. By the way, any of you who do HPLC often know that you use acetonitrile as a sort of non-polar solvent that's miscible with water. It's polar enough that it mixes with water, but it's non-polar enough to pull stuff off a reverse phase column, and you can see some of that effect here. Now, both of these are acids with negatively charged conjugate bases, right? So let's see how the value changes for a positively charged conjugate base. This is anilinium. Its conjugate base is neutral aniline. In water, the pKa of anilinium is about 4, and the reason that that's so acidic, most ammonium ions have pKa's around 9 or 10 in water. The reason it's so acidic in water is because the lone pairs on the nitrogen in the conjugate base are conjugated with the ring. Does that make sense? Do we need to draw that, or do you sort of imagine that? Okay. So acidity here means getting rid of the charge and going, I'm going to draw the neutral conjugate base anyway, sorry, and going to the neutral conjugate base. So what do you predict about the pKa's? Should the acidity weaken? Should it stay the same? Should it get more acidic? What do you think? Okay, Isabella, you think it should get more acidic? Why? Right, conjugate base is neutral and is probably more easily solvated by the nonpolar solvent. So in this case, it's not the conjugate base that doesn't get solvated well, it's the acid form that doesn't get solvated well in the nonpolar solvent. And therefore, it's easier to lose the proton to get to something that's neutral. Go ahead.
Is the pKa so low because the benzene ring delocalizes
The lone pairs. So the pKa is low not because benzene delocalizes the positive charge. Actually, you can't draw any resonance structures here where the positive charge ends up in the ring because this nitrogen is bonded to 4 things and it's fully saturated. However, resonance does stabilize the conjugate base because these lone pairs are delocalized in the ring.
Okay, yeah, so taking the proton off is stabilized.
That's right. Taking the proton off is good,
With
or easier.
With normal amines, it's like 10 or 11.
Right. Yep. So this is substantially more acidic than normal amines. Go ahead, Kim.
I guess I'm still struggling with this idea. Doesn't it matter where the proton is going to and whether the thing that it's going to wants the proton or not?
That's right. Doesn't it matter where the proton is going and whether the thing it's going to wants it or not? The answer is yes, but remember these pKa values. pKa is only defined for the following reaction, right? HA with water to give you A minus and hydronium. And then pKa equals pH, I'm going to get that wrong.
You could derive it from the English.
You're going to make me... Thanks, Kim. That's helpful. You can derive it from the equilibrium constant. Kim is right. You can indeed derive this from the equilibrium constant. And I'm sorry to be snarky. I should not have fed the snark this morning. Take that over there. Ka equals Keq times water. I've had other colleagues, Gen Chem colleagues, tell me that you may not do that with water's concentration, but Doherty and Anslin did it, so by golly, we can do it too. You put the number 55 molar in there because that's about how concentrated water is. And if that makes you uncomfortable, you can remember that these are all just activities anyway, and so any discomfort you may have will be relieved by the activity coefficients, which are important, but in practice we don't worry about them that much. Then you take the minus log of both sides. That gives you pKa minus log of H3O plus is just pH minus the log of, yeah, okay. So pKa is only defined for that reaction. So all those numbers are relative to water. So it's kind of imaginary because you couldn't actually do that reaction in water because of the leveling effect, or rather you could do it, but you couldn't measure it because we don't have analytical techniques that can measure one particle out of, I don't know, several trillion in water or something like that. So in any case, yeah, it's difficult to think, okay, what is that acid actually doing in that solvent? But for the purposes of comparison, all of these numbers are relative to water.
I guess I just need to go read that chapter about how to measure the pKa value.
Well, if you want to know, it's there. I skimmed that section, was like, my eyes are glazing over. And if I'm bored by it, at least some of the people in the class will be bored by it. So.
Chem 112, 113 for years in a row. So.
Okay, so you may wish to know this stuff, and that's good. More power to you if you wish to read that information. I will say that based on our discussion, the pKa actually goes down in DMSO. It gets even more acidic because DMSO is apparently less good at stabilizing that positive charged aniline ion. The pKa doesn't change as much in DMF. So this is why I'm saying you can't just say all acids are weaker in organic solvent. It depends on the acid. If the acid's the charged thing, then you may not see any change, or it may get more acidic. Okay? Go ahead.
Would it be possible to get this dissolved in even more nonpolar solvents like carbon tetrachloride?
Could you do even more nonpolar solvents? I don't know. At some point, you're limited by however you're measuring pKa and whether that thing is soluble in the solvent. So, yeah. All right. So here are some other trends. Let's see. Maybe we don't need to actually... Oh, I want to show you how acidity trends that we're used to in water are more spread out in, say, DMSO. And by far, DMSO is the solvent where these pKa values are, other than water, it's the most common solvent to have determined pKa values in. So as an example, the halide acid series in water, 3.2, then HCl is -8, HBr is -9. These absolute numbers don't matter, just the trends in DMSO. HF is, oh, sorry, wrong. In DMSO, HF has a pKa of 15, so way less acidic. HCl is way less acidic, and HBr is way less acidic. And this is just the exact same trend we observed before. Nonpolar solvent is a poorer ion solvator. Okay. And this also reflects the fact that the trends are more broadly spread out. As an example, you have, 11 pKa units there and 13 there, so it's a little bit more spread out. That becomes a little more dramatic when you compare pKa's of, say, acetic acid and phenol. In water, acetic acid is, again, 4.8 pKa, and phenol is about 10. Oh, hold on. We've already done acetic acid. I didn't actually want to do acetic acid. Sorry, backing off from that. Let's do methanol versus phenol. Methanol has a pKa of like 15.5 in water, whereas phenol has 10. We've rationalized that previously in previous classes because the negative charge on the phenolate ion is stabilized by resonance, whereas the negative charge on the methoxide ion is not. That trend will stay the same in organic solvent, but both of these will become way, way less acidic because DMSO is not as good at stabilizing anions. However, we go from a 5-unit difference to an 11-unit difference. And rather than say, wow, that's so surprising that they're that different, we should say, actually, the reason why they're that close in water is because water masks these differences because it stabilizes the negative charge because of solvation. So the punchline is the ability of water to stabilize charged species actually changes pKa's and makes them, first, more acidic than they would otherwise be, and then also smooths out differences. Finally, and this I thought was fascinating, if you have a conjugate base that's stabilized by resonance, organic solvent suddenly makes way less of a difference. So the following molecule is malonitrile. It sounds like maybe marshmallows that are probably poisonous, but I don't know. Anyway. I get a giggle. Okay, thank you, Kim. I got a giggle. You know, if you can't laugh with me, you're always welcome to laugh at me. I will take that too. What a loser. Actually, pKa's are the same because the conjugate base of malonitrile is stabilized by resonance with those nitrile groups. And there are other examples of that. But if the conjugate base is resonance stabilized, then solvation doesn't matter as much. Remember, solvation, I guess, is a strategy for spreading out electron density. You take something that's charged and you orient a bunch of dipoles around it, and suddenly it's like you've spread out that negative charge through space. If you're already doing that by resonance, then solvation doesn't matter quite as much. All right. Why do we care that pKa values change in different environments? We care because a lot of biological reactions occur in environments that aren't exactly water. So if you think about the enzyme active site in general, they generally occur inside a protein, or at least if near the surface in some cleft. So they tend to be more nonpolar than water. In any case, they are heterogeneous, meaning that it's not a uniform water environment. You actually have functional groups nearby, and you can have H-bond donors / acceptors, and you can even have charged groups. So we would expect pKa's to change in enzymes. We may not know uniformly how they should change because it will depend on the characteristics of the active site. As an example, I want to show you 3, or maybe just one, I don't know. I can show you 3. There are 3 examples from the text. Maybe we'll do a couple. They're all in the extended notes that I've posted on Learning Suite. This is an image I made from a crystal structure. Here is the PDB code if you want to go looking at it yourself. This is human lysozyme. And this is the active site. This is a residue in the active site of lysozyme. You can see that we're looking at it, down at it from the surface. And so you can see that, and in the crystal structure, there's actually a ton of water molecules surrounding this glutamate. But it's not completely surrounded by water molecules. You have some nonpolar side chains here. Also, one thing I noticed is this glutamate is actually at the C terminus of a helix, which is the negative end of the helical dipole. So, make a prediction. If you already are in a spot that has extra electron density, what do you expect for this glutamate? Should it be more or less acidic? Less, good, because the conjugate base should be destabilized by that dipole. And in fact, whereas the pKa of glutamate normally in water is 4.2, in the enzyme pKa of this residue, which I'm not sure how you measure it, but it can be done, well worked out enzymological methods. That sounded funny. pKa is like 2 units, pK units, 100 times less acidic. Okay. And then there's another one I guess I want to show you. This is from the enzyme acetoacetate decarboxylase. It actually used to be that this was using this enzyme was a favored method of making acetone until like the 60s, when it became cheaper and easier to make acetone from petroleum. I'll give you the PDB code in case you want to go look this up. And the key residue is this lysine, and you can see we're looking at it from the surface. You have polar residues on the surface, and then the lysine that's doing the chemistry is deep down in this, at the bottom of this cleft. Right here, they're showing you that here is a lysine bound to a substrate analog via an imine bond. And what this lysine does in the mechanism of acetoacetate decarboxylation is, here's acetoacetate. You form an imine with that lysine, and that makes it so decarboxylation can happen, because when it does, you can put a negative charge adjacent to the imine and it can be resonance stabilized. Forming that imine requires the nitrogen of the lysine to be in its neutral form, not its positively charged form. So whereas the pKa of lysine in water is usually around 10, here in the active site, the pKa is 5.9. So at physiological pH, this lysine is neutral, and that enables it to do the chemistry it needs to do. So, in 352, as we talked about enzymatic reactions, we frequently said, and the enzyme does this, and then we had crazy arrows with HA and A and B and so on. And we sort of used the enzyme as a catch-all hand-wavy thing that explained why unusual things happen. One of the major things enzymes do is they put residues in a non-aqueous environment, thereby changing their pKa, so you can do chemistry. And there are tons of examples of that we could get into, but we won't. Let's see. Maybe I can take 5 more minutes on acid-base stuff to talk about some gas phase acidity trends. In the gas phase, you can no longer measure pKa's because pKa is always about a reaction with water, and in the gas phase, there is no water for these measurements. Typically, this is done by, well, I don't actually know the analytical methods that are used, but what you end up using is a delta H for loss of the proton. Or if you wanted to start with the conjugate base, you can use something called proton affinity, which is basically the opposite of the free energy, or I'm sorry, the enthalpy to lose a proton. I won't draw the conjugate bases, you can imagine them. In water, just for our expectations, in water, the pKa's for these acids are as follows. The fluoro variant is most acidic. The chloro is a and the bromo are close seconds, and the iodo is least acidic. And we've typically attributed that to inductive effect due to a nearby electronegative group, and knowing that fluorine is more electronegative than chlorine, than bromine, than iodide sort of explains that trend. I will point out that the variation is small. This is less than a unit of pKa. So in water already, electronegativity doesn't make a huge difference for these alpha halo acids. Now, in the gas phase, the free energy for losing a proton, these are all positive numbers because it's unstabilizing to do this. It turns out then a higher number means weaker acid. The fluoro derivative is the weakest one, and the iodo derivative is by far the strongest acid. And that sort of blew me away. What the heck is going on there? I thought electronegativity was important. And actually, in the gas phase, with no solvation, polarizability matters more. And we talked about this before when talking about carbocation stability. Do you remember the bigger your carbocation, generally, the lower in energy it was, because nearby functional groups tended to provide some solvation for that ion. Similarly, iodo is bigger and more polarizable because its valence electrons are held further from the nucleus than is the very electronegative fluorine. And because of that, iodo can polarize its electron density to help spread out the negative charge in the conjugate base. And it can do a better job of that than can fluoro, because fluoro is small. Even though fluoro is more electronegative, it turns out when you're in the gas phase and unsolvated, polarizability and size matters more. Okay? Another example of that. Go ahead, Dakota. This is in kcals per mole. So 4 kcals per mole is, at room temperature, would be maybe a factor of 1,000 or so in equilibrium constant. So that would be maybe worth 3 pKa units. So the differences are spread out. Similarly, if you look at the series isopropyl alcohol, T-butyl alcohol, isopropyl alcohol, ethanol, and then methanol. In water, if you measure pKa's, oh shoot, I didn't write those numbers down. It's 19 and 15.5, and I forget where they go, but you've got the weakest acid here, and you have the strongest acid here. Maybe I did write those down. Turn the page. Okay, doesn't matter, but 15.9, 17.1. We've rationalized this in water by considering the conjugate base and considering alkyl groups as electron donating groups, right? And so if they donate electron density towards the negative charge, that should destabilize the negative charge. Okay. That tends, we've used that explanation, but in the gas phase, again, if you measure, and these will be proton affinity numbers of the conjugate base, except they won't actually, sorry. There'll be enthalpy change for loss of proton. It turns out that T-butanol is the most acidic, and it starts to go down from there, again with a 5 or 6 kcal per mole difference between the most acidic and the least acidic. Why? It's the same size and polarizability explanation. That in the gas phase with nothing else around, alkyl groups are fairly polarizable and they can adjust their electron density in such a way as to spread out the negative charge on the oxygen. So if that's true, then why do we see the opposite trend in water? It turns out that in water, in terms of solvation, size works against you. So in water, there may be an intrinsic sort of inductive donation because of alkyl groups, though that effect is small. The bigger effect in water is that those bulky T-butyl groups don't enable water to get as close to the negative charge as it would otherwise want to be. Sterics block water molecules from ideal solvation. Okay, so we've seen that the solvent is important, whereas in 351 and 352 we sort of ignored the solvent. In physical organic chemistry, we're gonna consider what solvent is doing. The rest of the acidity trends should be familiar and easy to understand, so I think we'll forego talking about them. I want to spend the last couple of minutes talking about something called hard versus soft acid-base theory for Lewis acids and Lewis bases. At the end of chapter 2 in 351, I remember telling my students that generally the pKa trends were good indicators for how reactive conjugate bases would be as nucleophiles. And that was generally true, though there were some troubling exceptions. For example, even though the halo acids, HI, has a pKa of like minus 13 or something, iodide is still a very good nucleophile. And that seems exactly backwards, right? Similarly, thiolates, negatively charged sulfurs, are very good nucleophiles. How can that be? The pKa of a thiol is much lower than the pKa of an alcohol, meaning a thiolate should be way less reactive than an alkoxide. And it turns out that there are a couple of, remember Lewis acid, Lewis base is sort of a HOMO-LUMO interaction. You've got filled orbital electrons delocalizing into an empty orbital. And there are two ways that that can be favorable. We're going to define energy of interaction between HOMO and LUMO. And remember, at this stage of the text, they haven't gone into all the detail that we went into in chapter 14. So you can think of this as maybe the amount of energy that the HOMO goes down when you have the interaction happen, when you combine the two orbitals. And they say this should be related to a core energy repulsion, which should be unfavorable and therefore positive. And this is just electron-electron repulsion as the two nucleophile and electrophile approach each other. Repulsion of maybe the core electrons. On the other hand, you have an electrostatic energy that comes from Coulomb's law, and that energy is equal to the charge on your nucleophile to the charge times the charge on your electrophile divided by 4 pi times the permittivity of a vacuum times the dielectric constant times the separation between the two. So one way you can get this interaction to be negative is to have a nucleophile that's negatively charged and an electrophile that's positively charged, and to have electrostatic attraction pull them together. Okay? And in that case, highly localized charges that can get close to each other is a good thing. Alternatively, another way you can get a nucleophile and electrophile to interact with each other is by having really good orbital overlap. And they've defined this at this point in our text as being equal to 2 times the orbital coefficient on your nucleophile, orbital coefficient of the HOMO on the important atom in your nucleophile, times the orbital coefficient in the LUMO on the appropriate atom in your electrophile, times a number beta referring to the strength of the interaction, and that depends on the identity of the nucleophile and electrophile. But here's the major point: difference in energy between the HOMO of the nucleophile and the LUMO of the electrophile. And I may or may not have that in the right direction. So we'll think about a sort of absolute value. Okay? So another way you can have a very favorable interaction is for HOMO and LUMO energies to be close. This is the case for soft nucleophiles and electrophiles. In contrast, the electrostatic attraction is the case for hard nucleophiles and electrophiles. Hard nucleophiles tend to have low energy lone pair electrons or low energy electrons in a highest occupied molecular orbital. So this would be like lone pairs on oxygen. Examples of hard nucleophiles include hydroxide, fluoride, actually water as well, and there's others that are listed in your book. Alkoxides. It turns out that some amines actually sort of count as hard nucleophiles. The hard electrophiles that are listed are all sort of ions or aluminum or boron derivatives, so I'm not going to write them down at this point. Soft nucleophiles, though, include higher energy lone pairs in a highest occupied molecular orbital. They're higher in energy because they're not on a very electronegative atom. They also include things that are very polarizable. And so in terms of the nucleophiles, you can think of thiols and thiolates, iodide, and some others that we can talk about another time. We'll come back to this, and you can refer to this table or list of soft nucleophiles versus hard nucleophiles. But remember, it all comes from, you can either have a favorable interaction because of tight and favorable charge, or you can have a favorable interaction because the orbital energies are close together. Yeah, Kim?
What exactly do they mean by hard versus soft? Like, is this like an alcohol reference, or like?
Is this an alcohol reference, hard versus soft? No, I think it comes from the idea that most of the soft nucleophiles are highly polarizable, meaning they're kind of like the sponge with water in it versus a marble with a drop of water on it. Okay, that analogy is not that great, but it's the polarizability that makes the nucleophile good, and the fact that the relative energy difference is similar. So I've got to end the class, though I will answer some questions. I just want to make sure anybody that needs to leave can, has to. We can pick that up next time as well. We're going to move on to chapter 6 next time, which is stereochemistry. Be ready for some crazy helical stereochemistry and atrope isomerism.